Good afternoon, everyone, and welcome back to CS307 Computer Networks. We will start off with chapter number 3, Transport Layer. This is the very first part of the lecture. In this particular part, we are going to basically cover a few important aspects related to transport layers, such as multiplexing, demultiplexing, UDP protocol, and the concept of sockets. Treat this as a revision for what we covered prior to your midterm exam, and once we are done with the revision, we'll move on with the actual transmission control protocol, or the TCP protocol. So moving on with the actual outline or the goals of this particular chapter, transport layer. The goals are to understand the principles behind transport layer services. In particular, we will be talking about multiplexing and demultiplexing of data, the issue of reliable data transfer between two end systems, flow control or congestion control. We'll also learn about practical internet transport layer protocols such as user datagram protocol or UDP, which we discussed in previous lectures, is a connectionless transport protocol. And in addition to that, we'll be specifically looking at transmission control protocol or TCP, which is a connection oriented, reliable transport protocol which deals with flow control as well as congestion control. Now, this is a brief outline of the actual chapter. We will look at transport layer services, or in general, what comprises of transport layer applications. And then we'll have a look at the multiplexing and demultiplexing issues. What do we mean by sockets? What are actual port numbers? And how is actual multiplexing and demultiplexing of data carried out over any transport layer connection? Bear in mind, this is the fourth layer of the OSI reference model, the transport layer that we are talking about. In addition to that, we'll look at some practical or actual protocol in terms of reliability. The very first thing that we target is unreliability. That is the ability to understand what is going to happen if we have unreliable data transport. So in terms of unreliable data transport, the main protocol that is in use these days is the user datagram protocol or the UDP protocol. So in section 3.3, we'll be covering user datagram protocol. Then we'll take a look at the principles of reliable data transfer. That is how the actual underlying channel between any end system or any set of end systems dictates the issue of reliability and what comprises reliable data transfer. Now, up until this point, from section 3.1 to 3.4 is basic revision. So this is what we had already covered prior to your exam, and this is going to be a relatively quick session that we are going to discuss these once again, so that you can revise the important concepts before we move on to the actual transmission control protocol or the TCP protocol. Okay. So in section 3.5, we'll formally start discussing the connection oriented or transport layer protocol. We'll look at the header or the segment structure. We'll look at how TCP accomplishes reliable data transfer. What do we mean by flow control? What is connection management or congestion control? And then we'll start looking at the different principles or the different algorithms that we have available for congestion control. Now, bear in mind, when we talk about different versions of TCP or the different flavors of TCP that are available to us, we actually talk about the underlying congestion control algorithm. That is what differentiates one particular TCP version from another. So you will come across terms like TCP Tahoe, TCP Reno, TCP Vegas. All of these different types of TCP protocols have the underlying congestion control algorithm that is different from each other, and that is what defines the actual working principle of each of these different versions of TCP protocol. Then we'll look at some general TCP congestion control algorithms as well, in addition to these three, and you will also be given one small assignment in relation to section 3.6 and 3.7, the principles of congestion control. So let's look at the difference between transport layer and your network layer in a little bit detail. In network layer, we are interested in the logical communication between different hosts or different end systems. Whereas in the transport layer, we are basically interested in logical communication between the processes that are running on those hosts. So you have one host computer that is trying to connect to a web server, let's say Amazon.com or the YouTube web server. Now, the identification of the YouTube web server as well as your host computer is by means of your network layer addressing or your IP addresses in general. And once data has been delivered to the host, then the transport layer is responsible for identifying which process or application this particular data needs to be forwarded to. So the transport layer in essence is logical communication between the processes that are running on these end systems. It relies on or enhances the network layer services. It is a vital component of your OSI reference model or TCP/IP model. How do we actually identify the processes? So you would have studied in the operating system course that processes can be identified by process IDs. But in addition to that, whenever you want to communicate with a particular process over the network, okay, or over the internet, let's say, then each of the process or the application is identified by something called a port number. You would have done this extensively in the labs as well. Combination of your port number plus the actual address of the host, the IP address of the host, is termed as a socket. Okay, so whenever we want to accomplish or facilitate communication between two different end systems, there is a sender socket and then there is a receiver socket. In your book, an analogy of a common household is given where, in the example, they have taken two different houses, Anne's house and Bill's house. So Anne basically wants to deliver a letter to Bill. In this particular scenario, your hosts are the actual houses, the end systems. The processes can be the kids in the each house. The application message or the application payload, as we say, is the actual letter in the envelope. Your transport protocol is Anne and Bill who demultiplex to in-house siblings. So everything is received by Anne and Bill, which are an analogy of the actual hosts. And once the host has received the message, then we need to multiplex or demultiplex the message to the multiple different siblings or the multiple different processes or applications in each house. So who is identifying the house? The house is being identified by the network layer, and the siblings or the processes to which these messages or data needs to be forwarded is actually your transport layer port number. Okay, so the network layer protocol is like a postal service. It identifies the hosts or the addresses of the hosts, and once the letter or the message has been delivered to that particular house or host, then it is the job of your transport layer to identify which be forwarded to. So this is a very basic analogy that is used in your book. The main idea or let's say the underlying concept to understand is that hosts are always identified by network layer, whereas the actual processes which are supposed to receive and send data or multiplex and demultiplex data is identified by the transport layer. And in the actual world, in the realistic networking environment, this identification is carried out via port numbers. So we discussed in class as well, there is an organization named IANA, Internet Assigned Numbers Authority, which is responsible for assigning fixed port numbers to each of your processes or applications. So just as an example, if you talk about DNS service, it is going to use port number 53. If you talk about HTTP, it is going to use port number 80. HTTPS is usually 443. Then you have FTP, which runs on port number 20 and 21. So there are a fixed range of port numbers that are called registered port numbers, and then there are unassigned or non-registered port numbers which can also be used as opening and receiving sockets. Okay, so if you have your notes handy, make sure that you revise the actual registered port numbers. I believe it is 1 to 1005, which is registered port numbers, and beyond 1005, these are non-registered port numbers. So there is no need to memorize it, but at least you should be able to identify what are the important port numbers for prominent applications that we use in everyday networking. Now let's take a look at section 3.2, which is multiplexing. Now let's take a look at section 3.2, which is multiplexing and demultiplexing of data. So this is multiplexing and demultiplexing of data, a slightly animated slide. On the multiplexing at the center side, we handle data from multiple different sockets. That is, we receive it from multiple different applications. Once we receive it from applications, we open up multiple different sockets, which is a combination of your port number plus the IP address of the host. We add the transport layer header, which is going to carry this particular piece of information, that is what port number we are using, and this can be later used for demultiplexing purposes as well. So in this particular example, you have a client PC which is connecting to a server, and the server is connected to another PC as well. So both the personal computers are basically exchanging data with your single server. How does the server identify which data belongs to which particular personal computer or which particular end system? That identification is carried out via the IP addresses of the respective hosts. Once the data gets back to the hosts, how do we identify to which particular process this data needs to be sent to? Then comes in the port numbers, which are given by your transport layer. The port numbers are going to identify the actual process. Okay, so demultiplexing at the receiver is going to use the same information. It is going to use the header info to deliver the received segments to the correct socket. Now this is a visual depiction of how demultiplexing actually works. On the right side you have a diagram which shows you a TCP or UDP generic segment format. So this is generic, this is quite general. At the very top you have a source port number and a destination port number. This is 16 bits each. Then you have other different header fields depending on whether you are using TCP or UDP. The actual fields are going to vary. And then you have the application data or payload. Once your host receives these IP datagrams or IP packets as we call them, each packet has a source IP address and a destination IP address, which, as I explained earlier, is going to identify the host. Then each of these packet carries one transport layer segment. Now the transport layer segment has the actual source and destination port number. The host uses the IP addresses, whereas the port numbers are used to direct the individual segments to appropriate sockets, which are open on either of the end systems. Your multiplexing or demultiplexing using socket numbers usually works the same way whether you are using TCP protocol or whether you are using UDP protocol. That is, whether you are using reliable or unreliable service. The reason is that each of the hosts can make use of reliability or non-reliability, but in parallel they can be using multiple different applications which are connecting to the internet. Okay, so as this particular slide shows, once you create or open up a particular socket on the sender side, on the receiving side, when the host receives, that is the receiver receives a UDP segment, it checks the destination port in the segment. Okay, this is the port number that we talked about in the previous slide, that is part of the transport layer segment. After receiving it, it directs the UDP segment to the socket or the application that is using that particular port number. Now, when creating a datagram or a packet to send a UDP socket, the UDP socket must specify the destination IP address, which will identify your host, and the destination port number, which will identify the actual application which is using UDP on that particular host. IP packets with the same destination or the port number but different source IP addresses and or different source port numbers will be directed to the same socket at the destination. Okay. Now this is something that we discussed in class as well. Moving on from connectionless to connection-oriented demultiplexing, the TCP socket itself is identified by four different pieces of information which are called four tuples: the source IP address, the source port number, destination IP address, and the destination port number. The demultiplexing action is carried out by the receiver uses all four values to direct the segment to the appropriate socket. The server host may support many simultaneous TCP sockets, that is multiple different applications or processes which are using using TCP protocol, and each of these can be identified by its own 4-tuple information. Obviously, if you are talking about the same host, then the IP address is not going to change, but the respective port numbers for each of the applications or the processes is going to change. Web servers have different sockets for each connecting client. Okay, so non-persistent HTTP, for example, will have different socket for each of the requests that it is processing. Now let's take a look at section 3.3, which is connectionless transport protocol or user datagram protocol. This is again something that we previously covered in the lecture, including the basic header format, the working principle of UDP, as well as what defines a UDP checksum. That is, how do we calculate a checksum. So a basic revision of these concepts once again. As I had explained in class, each of the protocols is defined or let's say explained in something called an RFC, a request for comments. Request for comments for or RFC number for UDP protocol is 768. The RFC itself is a standardized format of a depiction or a definition of the working principle of any protocol. So anybody who wants to develop a particular type of protocol or new protocol or a research-based protocol needs to basically include the standard format or the working principle of that protocol in an RFC. The RFC in turn is available on the internet. You can simply Google RFC 768 and that will give you all the definition and descriptions and the working principle which is related to UDP protocol. So what does this RFC state, or what is the working principle of UDP protocol? No frills, bare bones internet transport protocol. There is no formal handshake. It is supposed to be quite fast. It delivers the best effort service. UDP segments may be lost or they can also be delivered out of order to the actual application. Now, the best effort service basically means that if a segment is lost, then UDP is not going to make any effort to recover this lost segment. Okay. It is also connectionless, which means no handshaking between UDP sender and receiver prior to sending of data. And each UDP segment is handled independently of others. So let's suppose we are sending segment number 1, 2, 3, and 4 from the sender to the receiver. Let's suppose that the order of delivery is such that you receive segment number 3 and 4, but you do not receive segment number 1 and 2. As soon as you receive segment number 3 or 4, the receiver automatically assumes that 1 and 2 is lost. So 3 and 4 are going to be received and they are going to be forwarded to the higher layer applications. When you receive datagrams or segments 1 and 2 later on, then despite the fact that they have been received, they were received out of order. So UDP has automatically assumed that these were lost. So these are going to be discarded at the receiver and they are not going to be forwarded to the higher layer applications. Why is UDP so popular, or why is UDP being used? Because it is good for streaming or multimedia related applications. That is, when you are talking to someone or when you are watching a movie online, due to the sheer speed of streaming, due to the sheer speed of the frames per second, even if 1 or 2 frames go missing, you are going to hardly notice that there is going to be any effect on the user experience. So for those types of applications, UDP is quite important. Then DNS, because it requires a fast response from the root server, from the TLD server, from your local server. DNS also uses UDP protocol. 3 times UDP protocol, as I explained in class, and for the 4th time, if UDP is not working or you are not receiving a reply from the relevant DNS server, then you are going to use TCP protocol. Another protocol that we will cover during the course of this particular module, that is, if we get time, we are going to cover simple network management protocol. That is probably the last or the second last chapter of your main textbook. Simple network management protocol also uses user datagram protocol. Then you have reliable transfer over UDP. So the question that we discussed in the lecture was that if you are using UDP protocol and you need reliability, how can you accomplish reliability when you are using UDP protocol? Because by default, UDP is not going to offer any reliability. So under those circumstances, it becomes the job of the application itself to incorporate some kind of reliability, even if it is using UDP protocol at the transport layer. This is your UDP segment header. You have 32 bits, 16 bits for the source ports, 16 bits for the destination port. Then you have the length of the actual segment. This is in bytes. That is the length of the entire segment. including the header bit. Then you have the checksum, and then you have the application data or payload. This is your general format. So once again, on this particular slide, there is a slide revision. Why is there a UDP? Why do we need UDP? What is the point of having such an unreliable protocol? Because there is no connection establishment time, which can add significant delay to communication. It is simple to implement, that is low load on the processor, no connection state at the sender or receiver is maintained. A relatively small header size, as you can see on the left. There is no congestion control, so UDP can basically send as much data as possible and as fast as possible. Some of the pros of using UDP protocol. The UDP checksum, the goal is to detect the errors, example the flipped bits in the transmitted segment. That is, when you receive a particular segment used using UDP protocol, the idea here is to check whether the received segment was with errors or without errors. If it was with errors, we are going to simply discard it. If it was received without any errors, then we can process it and pass it on to the higher layers. What is the working principle? That the sender treats segment contents, including the header field, as a sequence of incoming 16-bit integers. The checksum uses one's complement of the segment contents, and the sender puts the checksum value into the UDP checksum field. The receiver side computes the checksum of the received segment and checks if the computed checksum equals checksum field value. If no errors are detected, we are going to process it. If errors are detected, let's say that we are going to discard it. Let's say that we are not interested in receiving any particular segment which has errors. So this is a particular example that we covered in class as well. You have to add two 16-bit integers. Once you add these two 16-bit integers, the result should ideally also be a 16-bit integer. If it is a 17-bit integer, that is, you are getting 1 as carryover, then we need to wrap it around. We need to basically add it to the least significant bit once again. Once we add it to that particular bit, the sum should come out as 16-bit integers, and this process continues until we get to a sum which is 16 bits. So work through the 2 or 3 examples that we did in class. This was the very first example. So in this example, when we add these two 16-bit integers, we get 17-bit integer. We wrap it around. The sum that we get is a 16-bit then. And once we get the sum, we take the complement of it. That is, we flip the bits, the respective ones and zeros, and we get the checksum value. So please go through the examples that we covered in class once again.